Hello, my name is Niklas Holzwarth. I'm from the German Cancer Research Center in Heidelberg. Today I want to present you the Two Tomography, freehand 3D photoacoustic image reconstruction of an optical pattern. But first of all, I want to introduce you to Patrick. Patrick is our group mascot and he just recently went to Berlin and got a little bit lost on his trip. But then he walked around a corner, he saw a street sign which said Goethestraße, he looked it up in his map and he immediately knew where he was. You may wonder what this has to do with medical imaging or photoacoustic imaging in particular, but we're kind of in the same setting. We acquire 2D image slices and we are not aware of the pose in our 3D volume. Also, we don't know globally where our image slice sits on a body, which could be beneficial for register photoacoustic images, for example, within an MR image. Both local and global knowledge of pose could have huge benefit for clinical applications. But first of all, I want to explain you how photoacoustic imaging works. In photoacoustics, we irradiate tissue with short pulsed near-infrared laser light. This light then gets absorbed by so-called chromophores. They thermoelastically expand, which leads to an ultrasound wave, which we can detect with a commercial ultrasound system. So with this light in and sound out approach, we can make functional imaging of parameters like blood oxygenation. Related work had focused on 3D probes, constrained movement of 2D probes, or optically tracked 2D photoacoustic probes to produce 3D photoacoustic volumes. But these solutions are expensive, bulky, and prone to human error. However, when we look in the field of ultrasound imaging, sensorless approaches have been developed based on specular correlation and could be improved performance-wise using deep learning methods. Unfortunately, photoacoustic images are speckle-free, so we thought we could introduce artificial speckles to encode the pose of the probe into a photoacoustic image slice. So we add a street sign to a photoacoustic image to set the image in context of three-dimensional volume. We called our approach to two tomography because we printed an optical pattern on a foil and we have attached this then to a patient, which gives us the guidance and the reference coordinate system. On the left, you see a patient with the tattoo. On the right of the slide, you see our reference frame. In the center, you see an image viewer. So if we now perform a photoacoustic scan on a wavelength where we can excite the tattoo, we clearly see the three absorbing dots of our first prototype. From these absorption points or the distances of these points, we can estimate the pose unambiguously. This pose information we can then use when we acquire a second photoacoustic image on a different wavelength. For functional imaging, for example, for a vessel, we can now use this pose information and set this functional image in our 3D reference frame. If we now perform a scan now sequentially, acquiring the pose information and the functional information, we can then compound a 3D volume and render it, where you can see now in the center. In red, vessel, and in blue, our tattoo. So our first prototype can be described with two coordinates. First of all, A0, which is the distance between the origin of our pattern and an image slice. And secondly, the angle, alpha, which is the angle between the central line and an image slice. Both coordinates can be derived from the distances between the left and the middle absorption point and the middle and right absorption point. So if we know these coordinates, we can calculate a transformation matrix where we can transform our 2D image slice into our reference frame. according to 3 degrees of freedom. So a rotation around the y-axis and translations around x and z. To conclude, we can apply an optical pattern we call T2, which encodes pose information in our photoacoustic image slices. From this pose information, we can calculate transformation matrices, which allows us to compound several image slices together, which then allows us to render three-dimensional volumes. In the first feasibility experiment, we printed a logo of the IPCAI, and within a shield, so we printed it on a sheet of paper and put it between of 2 gel pads. On top of the gel pad, we put our tattoo, and then we scanned over the setup. The rendered result you can see here now on the right. So it's very clearly readable letters in blue and a tattoo in green. A quantitative analysis of our approach can be found in our proceedings paper, where we compare our Two Tomography approach with an optical tracked baseline. You now may think this scan was performed very carefully, but we also did a careless acquisition of the same setup. On the left, you see a naive stack of images where we moved the probe back and forth and tilted the probe. And on the right now, you see compounded with our T2 approach. The logo is readable again, a little bit unclearer than with a careful scan, but still the compounding works even for those unrealistic careless acquisitions. However, our first prototype comes with several limitations. First of all, it does only allow to account for 3 degrees of freedom because it's a 2-dimensional pattern. So we have the requirement that the probe movement over the pattern is orthogonal, and we are assuming the pattern to be a flat surface. To account for 6 degrees of freedom, one could design a 3D pattern where we spatially separate 2 2D patterns. Secondly, if we have an uneven surface, the distances between the absorption point gets distorted. These could be tackled by a post-processing step. Instead of using the shortest distances between the points, we could calculate the geodesic distance, by example, approximate the skin between the points with a Bézier curve or spline. Or one could think about a semi-rigid pattern where we have a rigid flat pattern, and underneath we have a flexible gel pad which accounts for anatomical unevenness. Last but not least, I want to give an outlook onto multimodel image fusion based on our T2 approach. On the left, we now build together a phantom, where we have a phantom box. We put some wires in it, and then we filled the box with agar. We printed or put a foil on top, where we printed our tattoo, which you can see now in the image viewer on the right. And then we made a photoacoustic scan and rendered it in our image viewer, where you can see clearly the wires we put in the phantom. We then attached predefined locations, MR markers, which are set relative to our optical pattern. We made then a MR scan and registered those markers. We know where they were in the photoacoustic volume, and we saw them in the MR image, and then on the basis of this we can clearly see that the registration is possible in this approach. We can also qualitatively see a very good alignment between the photoacoustic wires and the MR wires. So if Patrick now sees a 2D photoacoustic image slice, he knows he can apply an optical pattern, a tattoo for it, and then can compound a 3-dimensional volume. So to sum up, Two Tomography encodes pose information in photoacoustic images. It's a very simple setup which could be easily integrated into clinical workflows, and also potentially enables image fusion between photoacoustic and, for example, MR or CT. So I want to thank you for your attention and also thank my group back in Heidelberg and want to acknowledge our funding.